We're going to look at a few examples about building quadratic models from verbal descriptions. Mathematical modeling is the process of describing some real-world problem or real-world phenomenon in terms of mathematical terms, usually in the form of creating equations, and then using those equations to help us understand what's going on and to answer questions about that context. Now, recently we've been looking at quadratic functions, and we know that the graph of a quadratic function is a parabola. And because of the shape of a parabola, it's either going to have a maximum or a minimum value that will occur at the vertex. And looking at the graph of quadratics, and specifically looking at this vertex, can help us answer questions that are referred to as optimization problems. And those are going to be finding that maximum or minimum value in the model. So in this first example, a marketing department at Texas Instruments has found that when certain calculators are sold at a price of P dollars per unit, the number X of calculators sold is given by the demand equation X is equal to 21,000 minus 150 times P. Now this idea right here, this demand equation, relates two variables to each other. It's going to relate P, which is the selling price of the item, and X, which is the number of units sold. Okay, so that's what this demand equation is telling us. It relates the price P of the item to the number of units sold. So we're going to answer a couple of questions about what's going on with the selling of these calculators. The first question is, find a model that expresses the revenue R as a function of the price P. All right, so revenue is the amount of money received from the sale of an item. And the formula that computes revenue is R is equal to X times P, where X is the number of units sold and P is the selling price of the item. Okay, so if you tell me how many units are sold and how much the cost is for each item, we multiply those things together and that gets us our revenue, which is how much money we brought in for selling that item. So keep in mind that revenue is different from profit. Okay, profit is going to be the revenue minus the costs that it costs for the company to build and design the item. Okay, so we're just looking at the revenue, which is the amount of money brought in. So the revenue is X times P, and then I have this wonderful demand equation up here that relates those two variables to each other. So what we can do is we want to write this revenue as a function of the price P, so we're going to swap the variable X out and use the fact that X is equivalent to 21,000 minus 150P. So I'll put that in for the variable X. And then I'm just going to go ahead and clean that up. So I'm going to go ahead and write this in function notation because now I have everybody in terms of the variable P. So I'm going to distribute through, so I'll get 21,000 P minus 150 P squared. Now if you wanted to flip-flop those two terms so that the squared term was in front, you're welcome to. Otherwise I'm just going to go ahead and leave it like that. So for part B, this is asking us for the domain of our new function R that we just found. So the domain is going to be asking us what values for P, that's our independent variable, can we have? Well, first thing, just look at what P is. So P is about the price of the item, right? So because it's going to be the price, it's got to be non-negative. So the first restriction that I'm going to have is that p has to be greater than or equal to 0. Now remember that p and x are related, so next let's look at x, where x is, as a reminder, the number of units sold. Okay, so because he's going to be the number of units sold, this value has to be greater than or equal to 0. Because I can't sell negative units. So we have that demand equation, which was 21,000 minus 150p is equal to x. And then we now know that x should be greater than or equal to 0 in this context for everything to make sense, which means then this expression right here, this 21,000 minus 150p, this also should be greater than or equal to 0. Because this expression right here is equivalent to x, and I know x should be greater than or equal to 0. So let's just go ahead and solve this. All right, so I'm going to move this 150p, this negative 150p term to the other side, so I'm going to get 21,000 is greater than or equal to 150p. We'll divide both sides by 150, so we get p on the right-hand side and 140 on the left-hand side. So I've got these two conditions then. I've got this one right here and this one right here. All right, so if I pull these together, this is going to get me my domain. Okay, so my domain is my indent pair. So the set of all values that p can obtain such that 0 is less than or equal to p, and then simultaneously p is less than or equal to 140. All right, so we've got our domain. Now this problem still has, 5 more parts we have to work through. All right, so we're going to move on to the next part, C. All right, so part C is asking what should the unit price be in order to maximize revenue. Alright, so this is going to start getting into those optimization ideas that we were looking at earlier. So as a reminder, our revenue function is R of P is equal to 21,000p minus 150p squared. So if you look at the function, we can see for my quadratic term right here, it's negative 150 is its coefficient. So we will have a downward opening parabola. And so because it will be a downward opening parabola, we'll have a max that will occur at the vertex. So maybe it's just as a quick sketch for what's going on here. So along my horizontal axis, we'll have my price P. Along my vertical axis, I will have my revenue. And just as a very generic sketch, I will have a downward opening parabola. And right here would be my vertex. So that's going to be then, what we're looking for at here is what price P will maximize our revenue. And then on the next question, we'll actually find what that max revenue is. So since we'll be maximized at the vertex, let's find the vertex. Now remember, my independent variable in this case is going to be P. Right? So P is equal to, and then our vertex formula will do negative B over 2A. So that takes the coefficients of your quadratic. So in this problem, my value for B is the 21,000. So I'll have negative 21,000 all over 2 times my A value, which is negative 150. So I'll have negative 21,000 over negative 3,000, and we do that division, we get 70. So what we just found is that the unit price should be $70. And that will maximize my revenue. So we just found that this price right here should be 70. So now the next question is, what is the maximum revenue? So we want to find the output if the input is 70. So we'll use our revenue function and we'll put 70 in for P. So I'll have 21,000 times 70 minus 150 times 70 squared. So you can pop that into your calculator and you'll get $735,000 is the maximum revenue that would be expected. And then the price that that maximum revenue occurs at is $70. Alright, so we have found our maximum revenue. So it's $735,000. So for part E, that part will ask us, well, how many units are sold at that price? So this goes back to your demand equation. The demand equation relates the units sold X to the price P. So the demand equation was X is equal to 21,000 minus 150 P. I know what value for P I want to use. It's my 70. So we'll put that in and we will then figure out X is equal to 10,500. So this is then telling me that 10,500 calculators are going to be sold at a price of $70. Or another way you could think about this one is if I'm going to bring in $735,000 as my revenue, and that amount of money is going to be split over calculators that are being charged at $70 a pop, I can do that division to figure out then how many calculators are sold. So 735,000 divided by 70 also gives me my 10,500 calculators. So it just maybe is an easier approach, a different way to think about it. Okay, so moving on to part F. Okay, so part F says graph the sky. So to graph, we already have our vertex from our earlier work, so maybe let's just find our intercepts. So if I set 0 is equal to my function, 21,000 minus 21,000 P minus 150 P squared. I can factor out 150p from both terms. I'll be left with 140 minus p. And because that's factored, I can now set each factor equal to 0 and solve. So if 150p is equal to 0, that means p is equal to 0. So that will get me one of my intercepts at 0, 0. If 140 minus p is equal to 0, that means that p is equal to 140. So that gets me my other x-intercept at 140, 0. Alright, so as a super dinky graph of what's going on here, let's go ahead and put down, I only need the quadrant 1 because everybody's going to be positive. So along my x-axis I have my price P, along my y-axis I have my revenue R of P. Alright, and this is not going to be to scale, but I'm going to have one x-intercept over here at 0, 0. I'll have another x-intercept over here at 140. Halfway between them is 70, and that's where my vertex is going to occur. And my vertex then will give a y value, that maximum revenue of that 735,000. And then we're just going to draw a parabola going through those points. I'm going to clean that up and try that one more time. Alright, parabola going through these. to the vertex, up to the vertex, and then try and have some sort of symmetry in here. Okay, so as one final thought on this, what if we wanted to try to graph this? And I'm going to graph this using Desmos. So in Desmos, I'm going to put in my function, and I'm going to use x as my independent variable as opposed to using p. So I'll have 21,000x minus 150x squared. And if I go to try to graph that on the standard window that they're giving me, we can see that I'm not seeing so much of the parabola. So I might be like, okay, well, I want to just, maybe zoom out, and you can use these zooming buttons right here. And okay, so there's where I'm seeing the other end of my parabola, but where's the top, right? And we know just from the work we've done so far that this top is going to occur at 735,000. And you can see if I keep zooming out, it's going to zoom out proportionally, and I'm still nowhere near my 735,000. And I'm starting to maybe lose my view of what's going on with this graph, right? So that's why it's helpful to maybe do some work on the side, so that way when you get to your technology you can set appropriate windows. So if I go up in here into graph settings, I can change my axis information. So I know I want to be here in quadrant 1, so maybe for my my x-axis, maybe I start that at, I don't know, -50, and I know I'm going to go out to 140, 0 for that other x-intercept, so maybe I'll just bring that out to 200, so my x-axis maybe goes from -50 to 200, just to kind of have a little bit of room on the either side of my graph. And my y-axis, I know I want to stay positive, but maybe I give it a little bit of negative stuff, so maybe -200. And then I need to go up to 735,000, so maybe I'll just put 800,000 just to have something nice and easy right there. So then we can see here is now I'm getting a really good view of my graph. I'm being able to see that vertex, and I can then also see my x-intercepts. If I maybe slide this and maybe zoom this out a little bit more, I have a little bit of a better window. Okay, so let's go back to our work and wrap up the last part of this question. So part E had asked what price, or prices as we're going to find, should we charge to get at least $675,000 in revenue. So I'm going to take my revenue function, which is the 21,000, p minus 150 p squared, and we'll set that equal to the revenue we want to achieve, which is 675,000. So then we just need to solve this quadratic equation. So we'll set it equal to 0. So 0 is equal to 150 p squared minus 21,000 p plus 675,000. And we'll find that actually every one of these terms is divisible by 150. So we'll just go ahead and divide that out, make things a little bit smaller. So we'll get 0 is equal to p squared minus 140p plus 45,000. Now with all the zeros, it might look a little intimidating to try to factor this, but we're really just looking for two numbers whose product is 45 and whose sum is that -14, because then the zeros kind of work themselves out. So the two numbers that would multiply to 45 but add to 14 would be 9 and 5, but because I need to build these bigger numbers as opposed to using 9 and 5, we'll use 50 and 90 to factor this. So that actually wasn't too terrible to factor, so then we'll set each factor equal to 0, so this factor gives p is equal to 50, and this factor gives p is equal to 90. So we could charge either $50 or $90 in order to get to at least 675,000. Now those values will hit 675,000 on the nose. Since it was at least 675,000, this could be then or any value in between. So maybe if we come over here to our graph to see what's going on. So here would be 50, and here would be 90. Okay, and then coming across over here, we'd be at the 675,000. Okay, so then we can see then that we'll hit our target revenue at those two values, but if I go anywhere between them, I'll be in this kind of upper region where I would be making more than the 675,000. All right, so that finishes example 1. Example 1 was a long question. It had a lot of different subparts. Let's take a look at our next example. So example 2, a farmer has 2,000 yards of fence to enclose in a rectangular field. What are the dimensions of the rectangle that encloses the most area? So it's always good to maybe start off with like a little picture of what's going on. So here's my rectangular field. All right, so here would be the length of the field, and here would be the width of the field. And this idea about this fence is going to connect geometrically to the idea of perimeter. Okay, so then we know that the perimeter of this rectangle needs to be 2,000. So the perimeter of a figure, you're just going to add up all the sides. So for this rectangle, I'm going to have 2 of the length sides plus 2 of the width sides, and I want that to total to my perimeter, which is my 2,000. The other thing that's going on in this question is it asks about enclosing the most area. So area of a rectangle would be length times width. All right, so I'm looking then to enclose the most area or maximize my area. So the first thing that we're going to do is we're going to write a function for area in terms of one of these two variables. Now it doesn't matter which one, but solve for one of these variables in your perimeter equation, either the length or the width, it doesn't matter. I'm going to go ahead and solve for the length, so I would have 2L is equal to 2,000 minus 2W, divide everybody by 2, I get L is equal to 1,000 minus W. So what I'm going to do for this expression for L is I'm going to drop it into my area equation. So then I would get area is equal to 1,000 minus W times W, and we'll distribute through, and then I'll have a function for area in terms of the width. So I get the A of W is equal to 1,000 W minus W squared. So now looking at that, we can see that this is going to be a downward opening parabola. If I were to look at graphically at what's going on, right, this is a quadratic, so it will reach a max area for some value of W. So let's find where that max value occurs. So we're going to be looking for the vertex again. Right, so for the vertex, the variable of interest here is W. So it's going to be, again, for the formula, negative b over 2a. For this problem, it's going to be negative 1,000 over 2 times negative 1, right, which would be negative 1,000 over negative 2, which then gives me 500. Sorry. Right, so the vertex occurs then at 500. That is going to be the width of the rectangle. Let's actually find what that max area is. So then A of 500, which would give me the area when the width is 500, is going to be found by doing 1,000 times 500 minus 500 squared. And you can pop that into your calculator and get 250,000. So what we just found then is that the max area of 250,000 square yards will occur when the width is 500 yards and the length is 1,000 minus 500 is equal to 500 yards. Just drawing a very simple graph of this to visualize what is happening. All right, so I'm going to have a parabola. It'll have x-intercepts at 0 and 1,000. and then at 500, I'm going to reach my max area of my 250,000. And this is actually a very interesting idea from geometry that says if you want to maximize area given a specific perimeter, you want to make a square if you're trying to keep some sort of like rectangular shape. And if you can even go to a circle. That will maximize area given a restriction on perimeter. Alright, so fun geometry fact, but to answer this question, the max area is the 250,000 square yards. Okay, so let's take a look at one last example. So this one was going to be about a projectile being fired from a cliff 500 feet above the water at an inclination of 45 degrees to the horizontal with a muzzle velocity of 400 feet per second. Now from physics, and we're not going to get into the physics behind there, but if you want you can take a physics class and learn all about it. From physics, the height h of the projectile above the water can be modeled by h of x is equal to the fraction negative 32x squared over the quantity 400 squared plus x plus 500, where x is the horizontal distance of the projectile from the base of the cliff. Alright, so first let's draw a little diagram of what's going on here so we can again visualize what's happening in the scenario. Okay, so here would be my cliff. Okay, so here is going to be the 500, and then from there, let me just draw a little dotted line from there, this projectile is going to be fired off. Okay, it's going to be taking off from here at an angle of 45 degrees. Okay, so that's what it talks about, an inclination of 45 degrees to the horizontal. Okay, so this projectile is going to be taking off. It's going to reach some sort of a maximum, and then it's going to come back down and hit the ground. Okay, so we're going to be finding the maximum height of this projectile, and then how far from the base of the cliff will the projectile strike the water. Now the first thing we're going to do on this is let's clean up this expression because that 400 squared in the denominator is not currently simplified. So h of x is equal to, and then I'm going to pull off this x squared and write it off to the side. So negative 32 over 160,000 x squared plus x plus 500. And then I can clean up this fraction a little bit more. So this will simplify to negative 1 over 5,000 x squared plus x plus 500. Right, now over here, the variable x is the distance the projectile is from the base of the cliff. And then my y value is h of x, or the height this thing is. All right, so we're going to be finding that maximum height. Okay, so I want to know what this value is right here. In order to find that value, we need to find this vertex. Okay, so to find the vertex, the x-coordinate of the vertex is going to happen at negative b over 2a. So it'll be at negative, and then my b value is 1, over 2 times my a value, which is negative 1 over 5,000. So I'll have negative 1 over, and then the denominator will have negative 2 over 5,000. Okay, and you could clean that up, that fraction, but I want to talk more about the fact that this is a complex fraction, right? It's a fraction inside of a fraction. So remember how to clean this up. The numerator fraction will stay, the division will change to multiplication, and then the second fraction will flip to its reciprocal, right? Because that's how you divide fractions, is you multiply by the reciprocal. So I'm going to take the reciprocal of this denominator fraction. So I'll have negative 1 over 1 times negative 5,000 over 2 instead. So that just simplifies to 5,000 over 2, which gives me 2,500. So what we just found is 2,500. this is the feet that the projectile is from the base of the cliff when it reaches that max height. So now let's find the max height. So that max height will occur at h of 2500. Okay, so in my function, I'll have negative 1 over 5,000 times 2500 squared plus 2500 plus 500. Right, and you can pop all that into your calculator, so you get 1,750 feet. Right, so that is going to be this max height that the projectile reaches. Alright, so that is my answer for part A. Now let's take a look at part B. So part B is asking us how far from the base of the cliff will the projectile strike the water? Well, this projectile will strike at the water. How that translates mathematically is that the height of the projectile will be 0, because it won't have any height from this horizontal. So we're in my h of x function. I'm going to have an output of 0, and we're going to figure out what are the x values that give me that corresponding output. Okay, so I'll have 0 is equal to negative 1 over 5,000 x squared plus x 5 plus 500. Now, because of that fraction, even trying to factor something like this is not going to be that great, so I'm thinking we'll probably use the quadratic formula. So for the quadratic formula, you have to identify your a, b, and c. Notice that this is set equal to 0, so I'm good there. But for the quadratic formula, putting in that a value being negative 1 over 5,000 sometimes can make the calculations a little bit complicated. Not impossible, just more complicated. So one of the things that's sometimes nice is to clear the fractions. Now in this case, because that denominator is so big, our numbers are going to get big, but hey, at least I won't have fractions, so maybe I'm trading one problem for another. But to clear the fractions, we'll multiply both sides of the equation by 5,000. So then I'll get 0 is equal to negative x squared plus 5,000x plus, and then, oh geez, on this side, we'll get 25 with 5 zeros after that. So is that 2,500,000? Right, so big number. But at least at this point in time, if I use this in my quadratic formula, my a value is negative 1, my b is 5,000, and my c value is this 2,500,000. So let's go find out what this x value is that would make this thing true. So I'll have x is equal to negative b, so negative 5,000, plus or minus the square root of 5,000 squared minus 4 times my a value, which is negative 1, times my c value, which is this 2,500,000. All over 2 times my a value, which is negative 1. Alright, so this gives me then negative 5,000 plus or minus the square root of, and then your discriminant is going to be 35 million. So 35 followed by 6 zeros, all over negative 2. And at this time, let's just throw this in our calculator and get our 2 decimal approximations. So in the one case, I'll have the negative 5,000 plus the square root of the 35 million all over negative 2. And in that case, we should get a decimal approximation of about negative 458.04. And in the other case, I'll have my negative 5,000 minus the square root of my 35 million. All over negative 2, and that one is approximately equal to 5,458.04. So because what x is going to be is the distance this projectile is from the base of the cliff, you cannot have a negative distance. So I can remove the negative possibility. So then we found then that this projectile will be approximately 5,458 feet from the base of the cliff when it hits the water.